read now. Okay, so questions on any and all. What you got, Mackenzie? Homework 8, number 3. Okay. Okay, so we have the solutions x equals -3/2. So if I add that over, I have x plus 3/2 is one factor. I have 5 with a multiplicity 2, so that means I'm going to get it twice. So I'll have x minus 5 equals 0, and I'll have 2 of those. And then I have x equals 1 plus root 2. So again, I'll subtract that over, and I'm going to think about that as one big chunk. Now, because I have that one, I know that because of the irrational conjugates theorem, I also have to have its conjugate, which I'm also going to subtract over. And then the last ones I have is, I had more than that, I guess. There are a lot of them for this one. I was pretty mean here. So I got that one. And again, a complex conjugate, so I know I also have to have this one. If I am doing anything and you're not quite sure of it, please, please, please stop me. And I'd be happy to slow down or explain some more or whatever. And I'm not going to write down 10 of those. I'm just going to write that x equals 0 as a multiplicity of 10 because jeepers creepers, that's going to be annoying, right? So far, so good, everybody? So now I'm going to multiply each one of these equations together. So I'm going to have x plus 3/2 times x minus 5. I'm just going to write that as x minus 5 squared rather than writing it 2 times. And x minus 1 plus root 2. And then x minus 1 minus root 2. And then x minus 2 plus I. Then x minus 2 minus 3i. And then I have an x to the 10th. So far, so good, Mackenzie? Yeah, if you do, I need to wait for a minute. I can slow down here for a minute and pause. That's okay. Again.
Is this the imaginary number that you need to do both the conjugates for?
And irrationals.
Okay.
So imaginary and irrational both have a conjugate. Okay. So the goal here, it says I have to have integer coefficients. So right now, I can't make an argument that I'll have integer coefficients until each one of the factors has only integer coefficients. So one way to fix that would be to multiply these ones with the conjugate pairs together. So when I do that, I'm just going to FOIL. So x times x is x squared. X times that quantity is that. Then I have this. So I'm going to have x times this quantity. And then I have those two quantities multiplied together. So far, so good? Okay, so I'll go ahead and distribute those negative x's through. Oops. It's minus. And then I have to FOIL this thing out, but I really don't have to because that's just the difference of two squares, right? That last piece. So I know it's just going to be like a squared minus b squared. So I'm not even going to bother with the foiling. You could if you wanted to. I'm just going to take that shortcut though. So those guys cancel out. And the square root of 2 squared is just 2. So 1 minus 2 is 1. I'm going to do the same thing now over here. And distribute through. Distribute through. And then, again, this is just a difference of 2 squares. So let's see, those guys cancel out. So I have x squared minus 4x. And then this is 4 minus negative 9. Remember that 3i squared is going to be 9i squared, and the I squared is negative 1. That's why it's negative 9. You guys remember that from first semester? So I really have 4 plus 9, or 13. And I'll pause here as it seems like a lot of people are in the midst of writing a lot of stuff down, because I did go kind of fast through things. So I'll pause here and let you guys kind of catch up. Does that sound good, Mac? Do people call you that?
Not really.
I'll be the first. What about Big Mac? You've gotten that one? How about Mac Truck? No.
Never that one.
Haven't heard that one. Okay.
Wait, that's so cool. With the 2 minus, like 3i squared, why would that be able to become like a negative 9? Because I thought that if it was an imaginary number, you can't define it with like a real number.
So 3i squared is 3i times 3i, or 9i squared. And remember that I squared is negative 1.
Okay, yeah.
So 9 times negative 1 is the negative 9, is how that gets there. Does that feel okay?
Yeah, I forgot about the negative 1.
Nope, it's okay. That's why. Now let's re-aggregate what we have. So now we have this, right? We still don't have integer coefficients, though. What's the issue? We're good here, 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 but not on that very first one, because it's got a fraction in there. Oh, fiddlesticks, right? Remember, this is still a polynomial that's equal to 0. So what am I going to do to get rid of that? Yeah, I'm just going to multiply both sides of that equation by 2. Now, it's okay to do that because it doesn't...
Then are we okay to keep it this long?
Yes. I don't need you to do any more combining. Once you have everything with integer coefficients, you're good. Mackenzie?
So then x minus 5 squared, you wouldn't have to.
Nope. You can just leave that the way it is. Again, if the factor has integer coefficients, that's enough, right? Because you can make the argument that, like, if everything has integer coefficients, when I multiply it together, all I'm going to be doing to the coefficients is multiplying and adding and subtracting integers, which is always going to give me an integer back, right? I can't add two numbers and get a fraction if neither of the two numbers were fractions to start with. So we're good there. That specific property is called closure. So we'd say that the integers are closed over those operations of addition, subtraction, and multiplication. But not division, right? Because you can take two integers, divide, and get a fraction, like 1 and 2. Does that feel okay there, Mac? Okay. Who's next? Maddie.
Can we do number 4?
Sure. More annoying. All right, so let's see. The first one is 3/5, right? What's the one? Do you have it in front of you?
It's 1 minus 3 square root of 2 all over 2.
Okay.
And then it's 5 minus I square root of 3 over 4.
That's okay. All right. So this one. That's right. And actually, let's take care of the fraction part right now. Might as well just do it here, right? No sense in having to wait later.
Mm-hmm.
And take care of it now if you want.
Could we have done that in the other one?
Absolutely. Here, we're going to, oops. And then again, this is irrational, right? Because of the square root in there.
Mm-hmm.
So I'm also going to need its conjugate. Okay with that?
Mm-hmm.
And if you wanted to, even here, we could get rid of the fraction. And again, let's take care of the fraction right now. And that hang around. Okay, so let's aggregate this stuff all together. Now it says no constant term at the end. We'll take care of that at the very end with a little argument that I still need to deal with, but I'm just letting you guys know that I'm going to ignore that for the moment.
So since it doesn't have multiplicity of a certain number, is it just going to go once?
Exactly correct. Yep. So we'll go and, just like before, we'll take these conjugate pairs and multiply them together. So just have some annoying FOIL. And just like before, distribute this stuff through. So these two pieces cancel out. 3 squared is 9. And root 2 squared is 2, and 9 times 2 is 18. So there's that piece. If you're right, 3 times root 2 squared. Make sure the parentheses are in the right place, but... And then we'll do the same FOIL over here. And then we'll do that same choop, choop, choop. And then again, difference of 2 squares. And those two guys cancel out. 25. And then I root 3 squared is just going to be negative 3. So that's going to be plus 28. Okay. And then it still says no constant term, right?
Yeah.
We still have that to deal with. Remember, that was one of the pieces in the original problem. So can you tell if this polynomial right now has a constant term?
There's no constant.
Sure it does. Because when I multiply the first parenthesis to the second parenthesis, I'm going to have to multiply the negative 3 times negative 17, right? And then I'm going to take that result and have to multiply the negative 17 to the positive 28, right? So at the end, I'm going to be left with a constant term. Everybody agree with that? So what can I do to get rid of the constant term without ruining the zeros that I worked so carefully to get? Okay, let's think about it this way. Give me an example of a polynomial that doesn't have a constant term. Anybody? Edmund. Okay. What do you notice you can do to that? Okay, factor what? So we can factor that, right? What does it factor to? This should be an easy one here, guys. Right? Everybody agree with that? Okay. Give me another example of something without a constant term. Anything. Let's do something with 3 terms. Just give me an example. Doesn't matter what it is. We'll get this going back in the right direction here in a moment, but since nobody had any ideas, we're trying to jog our memory and show you guys how you could go about figuring this out. So we'll start at the opposite end, looking at polynomials that have no constant term, and then look at what they look like when we factor them a little bit. So give me another example of a 3-term polynomial that has no constant term. That's an example, right? 7x cubed minus 6x squared plus 8x. No constant term there. Can we factor that? No doubt we can. How do we factor it? Yeah, we just take out a greatest common factor of x. Everybody agree with that? So let's look at these 2 examples that we've looked at. What do you notice is in common to both of them? There's a greatest common factor of x. Yeah, exactly right. So what should we add to our polynomial? A greatest factor of x. So if we go back here, we just put an x there. We know then that the result will have no constant term. Again, we multiplied both sides by x equals 0, right? We multiplied by the equation x equals 0, but that didn't change any of the factors that we had, right? All the factors that we had are still going to contribute to zeros, just like they're supposed to. But when we distribute everything out, the last thing we'll do is put that greatest common factor of x all the way through, and that'll wipe out any constant term we might have had at the end.
If there is a constant term, would you just distribute it to?
So, well, you're going to get some stuff, and one of those things is a constant term at the end, and then we'll distribute the extra that gets rid of the constant term. You know what I mean?
Mm-hmm.
So I don't know, I don't want to go foiling all that out because it looks like a nightmare to me, right? But what do you think, my artichokes? Okie dokie? No? Yes? Maybe? Is it all right? You're going to say something if it's not all right? It's okay to say something. We can explain it some more if we need to. I'm happy to do more, but we don't have to. It's up to you guys, whatever you need. Yeah, go ahead. No, you're done. Yeah, no. That what we wrote there at the end are enough for me. I mean, you could FOIL it out, but I don't need you to do that. I think the argument that we just kind of made to ourselves, where if there's a greatest common factor that involves a variable, indicates there's no constant term, is enough, right? I sold you on that argument earlier. Okay, if you buy that, then there's no reason to FOIL it out. Or at least I see no need in foiling it out, because it just looks like 20 minutes of tedious grinding that I don't need you to do. Right? Just looks like a lot of not fun. And you guys have better things to do than to spend a bunch of time like grinding through some really tedious polynomial multiplication problem. You know? All right. Anybody else? Add a yawn there. Yo, go ahead.
Can you do 17 on the review?
17 from the review? I sure hope so. Let's see. Oh, it's the same kind of problem? Okay. All right. Let's put that in there. Whoa, that's tiny. Okay. So let's oops. So I'm just going to go and cheat a little and go straight to here. Is that okay?
Yep.
All right. So multiply this out. And let's see, what's that give me? Squared plus 2x plus 7ix plus 2x minus 7ix, and then plus negative 2 squared minus 7i squared. And that's going to give me x squared plus 4x, and that's 4 minus a negative 49, so that's 53. Over here, what do we got? Let's see, 4x squared. Let's see, 4x squared minus 4x minus 2 root 3x minus 4x plus 2 root 3x plus 2 squared minus root 3 squared. So let's see, 4x squared x, and then 4 minus 3 is 1. I think that should be it. Does that feel okay, Alyssa? Sorry, I went kind of quick on that one. If I need to, do you need me to slow down or re-explain anything, or are we okay? Okay. I get carried away sometimes. If I do that, you can feel free to interrupt and be like, can you just pause for a minute? I'm not processing. I'm just blindly writing things down as fast as my hand will move, and it's all going in one ear and out the other. That's okay. Edmund?
Well, it's kind of
Everything that I'm writing is on PowerSchool. Or not PowerSchool, OneNote. Yeah, it's all in the content library.
Can you move it over?
Mm-hmm. So that would be a good final answer at the end. Yes, Edmund.
Can you do number 4 on the sheet 7?
Sure. This is 8, right? And this list is going to be ginormous. Let's see what we have. 1, 2, 3. Not 4 though, right? Because that's 10 and 20. So 5. Not 7, not 8. But we got 9. 10. Not 11 or 12 or 13 or 14. We do have 15, not 16 or 17. We have 18. Next one I think should be 27. And then we have 45, I think. And then, let's see, 54. And then 9 times 5 times 2, so 90 maybe is the next one. And then I think probably 135 and 270. I probably missed one in there. I hope nobody's gonna, but I was close. You have all of those, and you have that whole list divided by 2 also, because there's a leading coefficient. Now, all the even ones are just going to reduce down to something already on my list, so I'm not going to bother writing those ones. So I'm just going to do the odd ones over 2, which are not something already on my list. I suppose that's also a decent double check to make sure that I had them all, right? 270 by 2 is 135, 90 divided by 2 is 45, 54 divided by 2 is 27, 18 divided by 2 is 9, 10 divided by 2 is 5, 2 divided by 2 is 1. I think maybe I do got them all. So that's that list. Are you okay there? All right. If I go and I look at my graph, actually I know what this one looks like. I remember. I'm not going to graph it and look at it. So I had a straight here at negative 2.5, and another straight here that around negative 1.5, a straight there at positive 2.5 or 1.5-ish, and then I had a bend coming through there at positive 3. And if I looked real close, I think that the positive 1.4 and the negative 1.4, those were actually a little less than halfway, so I'm going to write them a little less because I tend to think that these two are irrational, especially because they're in a very conjugate pairy looking. This one is probably rational, though I certainly can't have 3 irrational things. They have to be an even number of them. And the 3 is almost certainly rational. Since I don't know for sure that the negative 2.5 and the 1.4 and negative 1.4 are rational or irrational. I'm going to just list them separately. I have 5 over 2, which is 2.5, and I have 3 over 2, which is 1.5 on my list of rational solutions. So I'm a little bit hazy, maybe, as to whether those two are actually on there or not. So I'm going to just list them all separately and not put any irrational things down there. Since if there are irrational things, it's either, it's something that, it's one of those solutions that I've already listed. So I'm not going to make a separate irrational category. I'm just going to do it that way. Does that feel okay? All right. So me personally, the one that I feel the most confident about is the 3. So I'm going to start my synthetic division with the 3 because I'm, quite certain that that's a rational value. Will somebody read me the coefficients for this so I don't have to scroll back and forth? It's so long. Okay, did we miss any zeros in there? There are not? Okay. I just figured I'd double check because I don't want to start and be like, oh, fiddlesticks, 3 times 67. Yuckarooskies, what's that? 201, I think. This is real embarrassing that I'm going to probably screw up my mental math in here someplace. I'm trying real hard not to, though, everybody. I just want you to all know that. 198, I think. Hey, look at that. All right. Pretty good deal. And I know this is going to work 3 times, so I'm just going to go bulldozing through on this. I'm going to keep a little bit of an eye to make sure that, I don't get something good along the way, but, I got a 7-term polynomial there. That sure's heckin' something good that I'm interested in. Again, whatever, too many terms, not interested in whatever that is, I'm going to go again. Three times 18 was 54, right? Uh-oh. What did I goof up here? Something. Right? Where did I make my goofarooski? Well, that would be the place. Since when is 6 plus 1, 5? Did you guys know that? Apparently they changed math on me, or I'm trying to change math on them. That looks much more reasonable there. What's that, do you think? Nope. Oops, 42. Okay, so that worked. Now, I don't know if negative or 3 is going to be used again, but feel pretty good that negative 2.5 is probably rational, so I'm going to give that a go. It's positive 5, negative 4. positive 10, that's negative 4. That's positive 10, that's 0. Okay. Now let's try doing 3 again, I guess. That's our only choice, right? But this isn't looking real great to me. So we're really stopping here at this point. So let's see, constant x, x squared, x cubed, x to the 4th. And now, hopefully, when you look at that gross formula at the end, you at least notice there's a greatest common factor of 2. Whenever you do a synthetic division with a decimal like that, you should end up with a greatest common factor. And I'm going to go ahead and do that with the 2, just to get rid of the stupid decimal. Okay with that? Now I'm left with this thing. It's got 5 terms. We don't have any good way to solve that or to factor this anymore, yet it can still be factored more. The point of this is to show you that even though as much work as we did here and as complicated as things got, still not perfect. It's still not the whole picture. And in fact, there's no good, fast algorithm to do this kind of factoring in general. But if I take a look at this, I can be kind of clever and see how to factor this. So what I'm going to do is I'm going to take this and think of it as x squared minus 2x. Because I see if I do that, I can make 2 grouping problems that should work out when I do a factor by grouping on there. This is beyond the scope of what I think that we are you guys to do. But I wanted to show you that this does factor some more. So that's the best we can do for the factoring. And the takeaway here is, if you have irrational factors and you have imaginary factors, and they don't match up in just the right way, you can be stuck with something that you can't factor at the end. And this is a problem where no matter what order you tried to do the factoring in, you weren't going to get something nice that you could do something with, like number 3, if you did the right order and stopped at the right place. You could factor it down to completion relatively easily, knowing that you had to do that, not obvious from the start of 3. And finding the right order was not trivial, it just was guess and check. Here, the order didn't even matter. There was nothing you could do with it unless you wanted to get pretty sneaky at the end. And really, the only reason I was able to do that so easily is because I knew what the factors were already, which is not, which is kind of cheating, right? Now, you might have said, okay, I have the 1.4 and the negative 1.4. That's probably the square root of 2. So maybe you could have said, I think there's a x squared minus 2 in there, and tried that. And that's a reasonable thing to have done also. And could have gotten it to factor that way using some polynomial long division. But that's the gist of it. And then, Edmund, I'm not going to bother with the last part of this where I have to set each piece equal to 0 and solve. I'm just going to omit doing that because I just don't want to, guys. Not trying to say that I'm lazy, but I'm lazy. Plus, we don't have that much time left. I still potentially need to check a bunch of worksheet 7. So, Edmund.
So we technically did not consider.
Yeah, so you can't do the synthetic division with irrationals. You cannot do it. It will not work. So unless you knew exactly that 1.4 is the square root of 2, you could do the synthetic division, make it work with the square root of 2, but it stinks. Because now you're doing like subtracting an integer from an irrational number. So when you do you're always going to have like a binomial term that you're subtracting, and it just gets really ugly and complicated. But you can't, it won't even work if you don't have the square root of 2. Like if you try to do it with 1.4, you're going to be left with some leftover at the end. It'll be a positive remainder at the end. So, yeah. If they're irrational, you're not going to get the synthetic division to work with it. Okie dokie. Will you see something that complicated on the test? Heck to the no, right? On a problem like this, it would give you something, nothing near this ambiguous or complicated that involves like, it'll be much clearer. Let me put it that way. It'll look more like the things on the review where it was fairly clear what was going on. This was quite ambiguous at points, so. All right. You guys ready to stop here? I feel good about stopping also. If you want to check in your 7, you guys can queue up at my desk and just walk by and we'll take those in if this thing wants.
Look, can I go to the bathroom?
Yes. Can you flip through your pages just so I can see them all, Mackenzie? Not that I don't think that you did the whole thing, because I'm sure you did. But just policy. Yo, Al, how you doing?
I'm good. How are you?
Good. How did your tournament go in Nebraska?
It was pretty fun. We didn't do too well, but it was our first tournament.
Well, at least you had fun, right?
Yeah.
Thanks, Eddie.
I did like the first 2. I made a valiant effort on the last 2.
Thanks, Sienna.
Like John, you did in 10s and you get no credit. I don't have a pencil right
How's it
now.
going, my dude?
Good.
Good. What's your name again?
Kaylee.
Kaylee. Sorry. I just was looking at you and I'm like, you're not in your seat, so I can't cheat with my seating chart, and it just blanked out of my brain. Hi, Grace.
Hi.
How are you?
I'm good. How are you?
All right. Thanks, my dude.
Alright, this.
Thanks, John.